In this video, we're going to develop the conservation of mass equation from the general form of Reynolds Transport Theorem. So the starting point for all of these conservation equations that we're going to look at is to first of all identify what is the quantity B. So for conservation of mass, the quantity B is the mass. So we just replace B with M everywhere in the generalized equation that we see a B. The next thing we need to do is identify what beta is. Well, remember beta is the amount of B per unit mass. So beta is just going to be equal to 1 for conservation of mass. So B equals M and beta equals 1. The next thing we do is identify the conservation equation that is going to tell us how the mass changes with time. So remember, this is the left-hand side of Reynolds Transport Theorem. Well, by definition, the rate of change of mass of a control mass with respect to time is 0. Because remember, a control mass has no mass flow rate across its boundary. So the amount of mass in the control mass never changes. So the left-hand side of the general Reynolds Transport Theorem will just be 0 because the rate of change of mass in a control mass with respect to time is 0. So that's what we need to do in order to write down the general form of conservation of mass for a control volume, is just substitute these three quantities into our conservation equation. So when we do that, we get this. So notice the left-hand side here is 0 because of this. The first term on the right-hand side, there was a beta inside of here in the general form. We've just let that beta equal 1. And the same thing in the surface integral. There was a beta in here, and we've just let that beta equal 1. So this is a general form of conservation of mass for a control volume that will work in every situation. There are 0 assumptions buried in this equation. Now, we often simplify this equation a great deal to apply it in different situations, but this equation itself has no assumptions attached to it. Well, in the last video, we looked at a simplified version of Reynolds Transport Theorem that talked about this surface integral, and that was called the uniform version of Reynolds Transport Theorem. Well, in some situations, we can apply that here. So conservation of mass with the uniform assumption applied would look like this. So notice the surface integral is replaced by a summation over the discharges of m dot for each discharge times beta, but remember beta is equal to 1 for conservation of mass, minus summation over the inlets of the mass flow rate at each inlet. So that's our uniform version of conservation of mass. So if we take a look at the meaning of each of the terms in this equation, remember what this means physically. This is the integral over our entire control volume of rho dV. Well, realize all of that together is the total mass of everything in the control volume. Because we have small volumes, multiplied by density gives us mass, and we add those up over the entire control volume. That's the total mass in the control volume. But we always have to remember that this term has a derivative out front here as well. So this is the rate of change of mass in the control volume. So this is the rate at which mass is accumulating in the control volume. So if that's a positive number, it means that mass is accumulating or getting bigger, maybe a tank filling up or something like that. Whereas if that works out to a negative number, it means the mass is reducing in the control volume with time. So a draining tank or something like that, perhaps. So that's what that first term is, the rate at which mass is accumulating in the control volume. Now, if we look at these other two terms collectively, we have mass flow rate at discharges as positive and mass flow rate at inlets as negative. So those two taken together are the net rate at which mass is leaving the control volume. So notice that those two things, this unsteady term and the net effect of all the inlets and discharges have to add up to 0 by conservation of mass. So if we have some positive number here, meaning that mass is accumulating in the control volume, then this has to be collectively some negative number, meaning the inlets are bigger than the exits. So this term is dominating. There's net flow into the control volume. So one of those is positive, the other has to be negative in order to balance out and give us conservation of mass. So that is a look at conservation of mass, both the most general form that retains the surface integral to account for the mass flow rate leaving the control volume, and also this uniform version that we're looking here. The next thing we're going to do is use Reynolds Transport Theorem to look at conservation of linear momentum. We'll do that in the next video.